Hello out there, welcome to this tutorial again on probability. In this video, we'll be looking at some miscellaneous problems. So we start with problem 1. 3 fair coins are tossed at once. By generating the sample space for the possible outcomes, find the probability of obtaining A. At least 2 heads, B. Exactly 1 head, C. Exactly 1 tail. So in the solution, we are going to generate the sample space of the possible outcomes. We have a S is a set of, since there are 3 fair coins, we can have all heads, we can have 2 heads and 1 tail, where head, and then tail, or we can have it as head, tail, head, or tail, head. These are the possible outcomes for 2 heads and 1 tail. And also we can have 1 head and 2 tails, so that we'll now have it as head, tail, tail, or tail, head, tail. That's the second arrangement for 1 head and 2 tails. And the third arrangement, tail, tail, head. And finally, we can have all of them tails. So we have T. These are the possible outcomes for tossing 3 fair coins, or it is still the same thing when you toss a coin 3 times, you still have the same possible outcomes. Now N of S now is 8. Since the coin has 2 faces and it is being tossed 3 times, it is 2 raised to the power 3, which gives 8. If it is tossed twice, it will be 2 raised to the power 2. The same thing for die. If a die has 6 faces, if it is tossed twice, it will be 6 raised to the power 2. That's how we got that for the previous problems on probability. Please check the description section of this video on our YouTube channel to get link to the playlist containing all the problems on probability. So now we go to a part of the problem. Probability of obtaining at least 2 heads. The least you can get there 2. So they can have 2 heads or 3 heads. So that in this case, we have 3 heads here. It's going to be in the event space of probability of getting at least 2 heads. 2 heads here, 2 heads here, 2 heads here. The rest are 2 tails and 3 tails. So that the probability of obtaining at least 2 heads will be 4 over 8. And that will give us 1 over 2. And that's the end of A part of problem 1. For B, exactly 1 head, meaning the head is equal to 1. So we go to the sample space and see where we have only 1 head. So we have 1 head here, 1 head here, 1 head here. And there are 3 of such outcomes. So we have it as a 3 over 8. And the C part of the problem, probability of obtaining exactly 1 tail. For exactly 1 tail, we have 1 tail here, 1 tail here, 1 tail here. The rest are 2 or 3. So the probability of obtaining exactly 1 tail will be 3 over 8. And that's the end of solution to problem 1. So we go to problem 2. For problem 2, a group of medical personnel comprises of 3 nurses and 5 doctors. 3 personnel are to be selected at random for a workshop. What is the probability of selecting A. all nurses, B. all doctors, C. 2 nurses and 1 doctor? This is an example of dependent event, because the probability of picking the first one will be affected by the probability of picking the second one, because by implication it is not that the first one picked has a chance of being selected again. So that is why we are going to treat it as dependent event. Therefore, in our solution, we have the number of nurses to be 3, number of doctors to be 5, and the total of the personnel 8. So the probability of selecting all nurses will be probability of first one nurse, second one nurse, and third one nurse. So we are going to treat it accordingly. And the probability of picking the first one nurse will be 3 over 8. So one nurse is gone. So we are now left with 2 nurses and 5 doctors. The probability of now selecting the second person as nurse again will now be 2 over 7, since there are now 2 nurses and 5 doctors, making a total of 7 after the first selection. So that will now give us times 2 over 7. Then we are now left with 1 nurse and 5 doctors, making a total of 6 after the first 2 selections. So the probability of picking the third person to be nurse will now be 1 over 6. So simplifying this, we have it as 1 over 56. So we now go to B part of the problem. So probability of selecting all doctors. In the same way, it is going to be probability of the first person doctor, the second doctor, and the third doctor. So the probability of picking the first person doctor here will be 5 over 8. And the next one will now be 4 over 7. That's times 4 over 7. And the third doctor will now be what? 3 over 6. So if we simplify this, we have the probability of selecting all doctors to be 5 over 28. Then we go to C part of the problem. For C, the probability of having 1 nurse, that is the probability of selecting 2 nurses and 1 doctor. That's going to give us a probability that the first one is nurse, the second one is nurse, and the third one is doctor, or probability that the first one is nurse, the second one doctor, and the third one nurse, or probability that the first one is doctor, the second one is nurse, and the third one is nurse. So if you look at it again, you discover that there are 2 nurses and 1 doctor here, 2 nurses and 1 doctor, 2 nurses and 1 doctor. It is only the arrangement that keeps changing from one to the other. So we are going to employ the method of just solving 1 and multiply by 3, so that the probability of getting the first one nurse will be 3 over 8 times the probability of the second one nurse now again will be 2 over 7, and the probability of getting the third one doctor will be 5 over 6. Then we said we are multiplying by 3 because everything is still going to be the same thing. It is just that the numerators keep changing. So we just multiply by 3 over 1. So simplifying this, we have it as 15 over 56. And that's the end of solution to problem 2. We go to problem 3. For problem 3, the probabilities that Aaron, Adam, and Angela solve a maths problem correctly are respectively 2 over 5, 5 over 7, and 7 over 9. Calculate the probability that A, none of them solves the problem correctly, B, only one of them solves the problem correctly, and E, exactly 2 of them solve the problem correctly. In our solution, we need to get the complement of each of the probabilities so that we represent them with A, B, C since they are all A. So we can just say Aaron solving it correctly is 2/5, and Aaron not solving it correctly, which is the complement, is 1 minus 2/5, which will just give us 3/5. Then we use B to represent Adam solving it correctly, and that gives 5/7. And the complement, which is Adam does not solve the problem correctly, will now be 1 minus 5/7, and that gives 2/7. And finally, the C, which is representing that Angela solves the problem correctly, 7/9. So that C complement, which means Angela does not solve it correctly, will now be 1 minus 7/9, and that gives 2/9. So we start from A part of the problem. Probability that none solves the problem correctly will be A does not solve it correctly, B does not solve it correctly, and C does not solve it correctly. So which is going to be the product of the probabilities. That's going to give us 3/5 times 7/2, then times 2/9. Simplifying this, we have 4/105 in the simplest form. Then we go to B part of the problem. The B part of the problem says only one of them solves the problem correctly. So since it is probability of only one solves correctly, what we do now is it is either only A solves it correctly, B does not solve it correctly, and C does not solve it correctly, or A does not solve it correctly, it is only B that solves it correctly and C does not solve it correctly, or A does not solve it correctly, B does not solve it correctly, it is only C that solves it correctly. So these are the possibilities, and please, the idea of solving 1 and multiply by 3 is not obtainable here. So we are going to solve everything. The probability of A solving it correctly is 2/5. And the probability of B not solving it correctly is 2/7. So we have times 2/7, then times 2/9. All means plus. So we add. The probability that A does not solve it correctly is going to give us 3/5. And B solves it correctly is 5/7. And C does not solve it correctly gives 2/9. Then plus probability that A does not solve it correctly, 3/5 times 2/7. Then the probability that C solves it correctly is 7/9. So I want to maintain the same denominators. So I have 8/315. 5 times 7 times 9 is 315, plus 30/315 plus 42/315. So since they have the same denominators, we just add the numerators, giving us 80/315. And in the simplest form, we have it as 16/63. And that's the end of solution to B part of the problem. For C, we have the probability that 2 solve correctly. So in that case, we still look at the different possibilities. The possibilities are A and B solve correctly and C does not solve it correctly, or A and C solve correctly and B does not solve it correctly, or B and C solve correctly and A does not solve it correctly. So that in our solution, we have probability that A solves correctly, which is 2/5, times B solves correctly, 5/7, times C does not solve it correctly, will be 2 over 9. Or means plus. The probability that A solves correctly will be 2 over 5 times B does not solve correctly, 2 over 7, and times C solves correctly will be times 7 over 9. Then plus probability that A does not solve it correctly is 3 over 5 times B solves correctly, 5 over 7 times C solves correctly, 7 over 9. I still maintain the same denominators. So we have the numerator for the first set, we have 20 over 315 plus 28 over 315 plus 105 over 315. That's 21 times 5. So adding the numerators, I have 153 over 315. This is divisible by 9, or in the simplest form, we have it as 17 over 35. And that's the end of solution to miscellaneous problem 3. We might likely come with the second video on miscellaneous problems. Here we are drawing the curtain for the end of this tutorial. Please check the description section of this video on our YouTube channel to get a link to the playlist containing all the problems and videos on probability. Make sure you like and share this video. Remember to subscribe to our YouTube channel if you have not done that. Until I come your way again, goodbye.